Very good. So, to begin now with the content stuff, when we want to apply deep learning, it is very important that we switch to a framework that is somehow better than just coding everything in Python itself. Why is it so? Because deep learning still is very, very computationally intensive. For example, Facebook, when they are building new models, large-scale models, and they probably have more or less the best computers at hand that you can have for this, they still need, for some models, several months just to train the model. And of course, this is very, very computationally expensive, and if you want to apply deep learning in any given setting, you have to think about ways how to optimize your code and how to optimize the computational costs. And TensorFlow is a framework that was developed by Google, which is built exactly for this. So the main idea about TensorFlow is that any kind of computation is first represented in a graph structure. So this means you have nodes for your variables, and these nodes are connected with edges, and only if there is an edge between two nodes, data flows. This is why it's called TensorFlow, from one node to the other. And if you create first a kind of graph for the calculation, this is very useful for reducing the computational costs. Why is it? Because in many parts of the graph later on, of your computational graph, are independent from each other. And this means if the computer knows from the beginning what is going to happen in this graph, the computer can automatically decide, okay, we can take this part of the graph and calculate it separately from the other graphs, other parts. And therefore, you can parallelize your data, your computational process much better if you have a graph structure. Second point is, it's always a problem, as you probably know as computer scientists, when you are building a program and you don't know the size of the data you want to fit in the program. Because then your computer can't do anything else but reserving a huge space in the memory, because the computer doesn't know how much data will be put into there, and you have to reserve a huge space of your memory, of your precious memory, just for the possibility that there might be, this variable might be in 64 integer and not a 32 integer. So this is the second reason why it's really more effective to use a framework like TensorFlow, because then all the nodes in the graphs are already defined, and the computer knows quite well how much memory do I have to reserve for which node. And this again is very important for parallelization as well, because especially parallelization on GPUs have many, many cores, but they don't have much memory. So the computer has to know which part of the graph could be sent to a GPU if you have a GPU device. And if you can specify all this up front, then your computational costs are sinking very, very much. So this is the computer science reason why it's a good idea to use TensorFlow. And then there's the applied deep learning reason. TensorFlow is really something like the standard right now. Everyone is using TensorFlow, besides the Facebook people, because they build coffee and all these other stuff. And there are other frameworks you could use, but TensorFlow is really becoming, and within several years, I think it was, I don't know when it was published the first time, or it could be 2015 or something like this. I would have to look it up, but it's not on the market for many years. It's open source, and it has become really something like the standard in deep learning. So if you later would like to go to a company and I'm a data scientist and I can do deep learning networks, they probably expect you to work with TensorFlow and not to code everything in C, which might be even faster if you can do it, but the coding process normally takes long. And in any kind of application setting, normally it's very, very important that you're working together with other people in a team. This is one reason why I said it's very good for you to team up in this seminar as well. And as soon as you're working in a team, you cannot normally you cannot expect everyone else to be a very, very good native C coder. So probably you will have to focus on a framework more people are familiar. So this is the reasons for TensorFlow, and let's just dive into it and see a little bit how it works. So TensorFlow, as I said, is a framework. It's like an API. You install it like a normal library in Python, and then you can integrate it like a library with import TensorFlow. Normally, in all the examples, because you don't want to write TensorFlow, you just import TensorFlow as TF, and then you can have all these additional functions that are predefined in TensorFlow. But the point is, it is on the surface, it looks like it would be just a library that you are integrated into your Python language. It's not really true because the computations are really not made under the hood of Python anymore, but under the hood of TensorFlow, which means that they are compiled directly into C, and you have all this parallelization stuff. So even if you don't notice it, by using it, the moment you install TensorFlow and you're running your code in a TensorFlow environment, there is under the hood, it changes really a lot what the computer does in the end. It's not that it's still the normal Python thing, even if you can just exit it anyway. So in this first example, and the whole code here is taken from this excellent book. I really can recommend it if you want to get a touch of how to apply deep learning networks. It's called Learning TensorFlow, a guide to building deep learning systems. It was released, I think, in 2018, so quite in 2017. Nevertheless, it's quite new. It has a lot of very interesting examples in it, and the idea of this book is to level your code on a really production level. So many things like how to use scan functions and very sophisticated stuff in TensorFlow are described in this. This code is taken from there. So what is happening here? Well, it's first just an example what is meant with graph structure. So we define, let's say, our variables, but you see they are not called variables, but they are called TensorFlow constants here. And this just means we have some in this case, scalars, where we just have the numbers 5, 2, and 3. And then we can add an operation like to multiply or to add or to subtract, and these then are functions, calculation functions. So it's very, very simple. At this point, we take our constants A and B and multiply them, and this becomes the value of D. Then we take our constant C and add the value of B and subtract E from D, and so on. So, but the important thing now is this is represented at the computer as a graph. For example, if you are looking at C and E, this means the value of E is dependent from the value of C and from the value of B, because it was added here. But the value of E is not dependent from the value of A. So any calculations that are done with the value of A, even if they will come deeper down in the code, could be made separately from the calculations of the value of E. And this is the idea. So this is why I said it's sometimes it's a little bit, yeah, you don't know why do I have to do all this? Why couldn't I just program it in Python in a simple way? So the point is, in TensorFlow it's represented in a graph, and this graph means that you can separate parts of the graph which are independent from each other, and this is very good for parallelization. TensorFlow always works like this, that you predefine all your things and then you start a session. So here you define a session and then you have to run the session, and in this session you're just passing the value of f, and now when you run the session, TensorFlow is calculating all these, it's trying to calculate f, and to calculate f it has to calculate d and e, and to calculate d it has to know the values of a and b, and so on and so on. So when it's calculated, the operation goes from the end of the graph to the front to get all these information. And then, yeah, you get an output in this case. It's just the result of this very simple calculation. But as I said, the important thing about this is you have to think about this graph structure and why is it done. The reason is parallelization. And here we see we have normally default graph. So when you're starting TensorFlow, there is already a skeleton graph, an empty graph, but you can add new graphs to it. So you can define your own graph. In this case, we define graph G, which is empty as well, but now we have two graphs, and then we can use different operations in different graphs if we want to. So in this example now we have our constant A, and then A has a graph attribute that you can see in which graph is it. In this case we ask, is A in the graph G? And the answer is false. But is A in the default graph? Then the answer is true. So this is just to demonstrate that different variables or placeholders or whatever can be put in different graphs. So you can have different computational structures at once running in TensorFlow. And quite typical for any kind of TensorFlow program is the with command, because you can use it to say, in this case, for example, we have two graphs and we want our G2 graph to be used for a calculation or whatever. In this example, still it's about the question, it's just what is the default graph, and we can ask, is G1 the default graph? And then the answer is true. But we can, if we use the with command and say with G2 as default graph, now what is the default graph? Of course it's G2 then. But the interesting point about the with statement is that it of course only is relevant to all the comments that are connected to the with. And as soon as this whole paragraph here would be over, then of course you're switching back to the default graph that was specified. And this, for example, means that you can have different sessions running in TensorFlow. So it isn't only, it's not only relevant for the graphs that you're using, but you also could run different sessions on the same graph. Talking about sessions. So, as I said, TensorFlow is always, you first construct a graph, and then you run it, meaning all the calculations that were defined in the graph are really made by the computer. And you can either just when you call a session, where is it here? We call our session TensorFlow session as ses or session. We could either just say, and when we run this session, we provide the following constants, variables, all the things we need. Or you could use the fetches command, which just means that you are taking already defined variables within the session that is already defined then, so that you can use the same variables from different sessions and just integrate them into your session that you want to have right now. Yeah. We have our nodes as operators and edges that are tensor objects. So our different data structures. Here in the first example, C is defined as a constant, and it has the value 4. So the important point is when you the difference between tensor the difference between a TensorFlow object and normal object is that, as you can see here, the TensorFlow objects are always constructed as a tensor, and this means a tensor is a multidimensional array, as you probably know, and this is why the whole thing is called TensorFlow, because it's it makes the tensors flow into the graph. So what you're entering into the graph normally, if you're not really changing anything very deeply in the TensorFlow structure, would be a tensor, and a tensor is a multidimensional array. So here, every tensor has a value. In this case, it's a constant, and it has a shape, and it has a data type. And this is what I was explaining up front. So by defining these TensorFlow constants, instead of just defining a normal Python object, you are telling the computer already how many bytes should the computer reserve for this object, and you can change the different data types. So, for example, you could change the data type from float 32 to float 64, and so on. This is what we're doing here. It's the same constant, but we call it not only with a value, but we say this constant should be of data type float 64. And for example, now there is a very cool framework by Google where you can submit your deep learning networks, and Google is then automatically optimizing your TensorFlow graphs in a way, for example, that they exchange the data types so that less bytes are reserved where they are not needed. This sometimes leads to a little loss in accuracy, but the idea behind this is that even if you have a very complicated model, it would be very nice if you could run, for example, just on a smartphone, on a very simple computational device. And you can imagine as soon as you start to reducing the size of your data types, then suddenly you have models that were quite complicated to train, but they are not complicated to let them run. And you can let them run on our modern smartphones. So you probably know the NumPy library. NumPy is for numerical calculations in Python, and it's very NumPy and TensorFlow work together very, very well. And most of the time, you will probably use NumPy as well as TensorFlow. What you can do is you can have a TensorFlow constant and put into this constant a list. In this case, we have a list with 2 elements, and the elements are a list as well. And then this list is already directly interpreted from the TensorFlow library as a 2-dimensional array. So when you're looking at the output, it's a Python list input, but our dimensions are 2 and 3. And we can do this, of course, with more dimensions, as many dimensions as we want to. Here we have a 2 by 2 by 3 NumPy array. Yeah. This is very important because when you're looking under the hood of these deep learning algorithms, normally what you're passing around is really just multi-dimensional tensors, which could be vectors, or which could be matrices, or even 3-dimensional, 6-dimensional, whatever arrays. For example, when we are talking about natural language processing, we might have an array that has as 1 dimension the number of the words in a given sentence. So in each sentence has, let's say, 10 words or whatever, and these words then have different values, but we might add another, then we have a 2nd dimension for each sentence. This is our normal table we would have, but then we might add another dimension, for example, for the post tags that come from our natural language processing tools. Or in computer vision, you normally have each pixel as 1 element of these tensors, and for example, for each picture, you have 1 row in an array with all the values of the pixel. Then you have a 2nd row for the 2nd picture, and so on and so on. And you have an additional dimension for the blue color values, or for gray color values, and so on. Yeah, here the code is not so important. It's just to demonstrate that you can integrate things from NumPy, like mean and standard deviation, and plot different random number generators. So if you have a close look at the code, you will see most of the code is just for plotting this stuff. So it's not really important for us right now to see what there is happening. It's only what is happening is really just the beginning of this big part of the code. So what is happening? We have a session, a TensorFlow session. Then we have our mean and our standard deviation. They are set to 1 and 0. Then we call the random normal function and the truncated normal function, 50,000 elements, and a uniform distribution is created here. So we need for a uniform distribution in minimum value and maximum value. Then we can create our uniform distribution, and then the session is closed, and then we define all the things we need for the plots. But this is really not about deep learning, not really, but more about using the matplot library. Yeah, more or less the same here. You have many different functions in TensorFlow. For example, linspace is just giving you, you just define the beginning and the end. Here it's 0 and 4, and you will say, I want to have 5 values between these values, and then they are separated in the same distance. So it's a linear space operator. But more interesting is what you can do with the whole linear algebra things, because this is very important for what's going on in the deep learning algorithms in the end. For example, we have our constant A, which is of which dimension? Constant A? As which dimension? 2 times 3, exactly. And we can, which is very important for debugging, just plot the shape. And we did this here, so our first is the shape of A is 2 by 3. And this is exactly the dimensions of our constant. This is so important because in deep learning, you probably change the dimensions of your tensors many times because, for example, in a convolutional network, you want to take the whole picture, but then you don't really take the whole picture, but you just take a part of the picture and go scan over the picture in a special window size. And the results from these layers then are put into normally a picture that has a quite lower resolution than the beginning picture. So you're changing the dimensions of your tensors. And this leads all the time to many, many mistakes in programming. And then you get an exception, nothing works anymore, you don't know why. And this is why the getShape function is so important, that you can see what is really going on at which place and what are the dimensions of my tensors. So we have a second constant with and this is interesting. Here it is defined as just a list of 1, 0, and 1. So what do you think is the dimension of x?
It's three-dimensional.
Yeah.
It's a vector.
It's a vector with 3 elements. So, but the point here is it's really taken as a vector. So there is no information about the second dimension. But you could, of course, if you now would like to do a matrix multiplication, this is not enough. You cannot, we have our A matrix with this 2 by 3, and of course we could multiply this matrix in matrix multiplication with a vector, but therefore we have to tell the computer that here we have another dimension, because otherwise the computer cannot recognize that it is of a dimensional space that you can do a matrix multiplication. And you can do this with expand divs. And the one in this case, you can have a look at the documentation. You can have a one which is adding one dimension on at first place. If you have a multi-dimensional object, you could use, for example, -1, then you start from behind, or you could use -2 and enter a new dimension within already given dimensions, and so on and so on. And then after we have added this dimension here, then we can make our matrix multiplication. So we have a 2 by 3 matrix, multiply it with a 3 by 1 vector. What should be the dimension of our output then?
2 by 1.
2 by 1. And this is exactly what we have. Surprise, surprise. Very useful for remembering what is going on in your complex graphs are names. So what you can do is, more or less with every TensorFlow object, you can just give it a name so that you can call it by the name, and we will use later on, there is a second library connected to TensorFlow, it's called TensorBoard, which is a very strong tool for visualizations. And there it's very important that you name your object so that you can, for example, you could, here we just created calculational graph, but in TensorBoard we then could have a look on this graph. And if we give meaningful names to our objects, then we can identify what is going on. And as you see here, you can give the same name to different objects, and then it's just expanded to see under one. But you also could define a name scope, and this means that here in this example we define a name scope prefix name, so all the names that are given up in this with statement now automatically get the prefix name as the name scope. This is quite handy if you are building complex graphs. So until now we worked with constants in TensorFlow, where we say what the value should be, but of course there are also variables as well. And a variable just means that it has the value of this variable can change, might be depending on other things. And yeah, this is what you see here. We define a variable, and then our output just gives us the shape and the data type. But after we run this little code, and we're just giving random normal numbers to this variable, after this code, when we call the variable, we of course get the entries that we make. A little bit complicated and sometimes annoying is when you have a session and you run the session and then run the session again, a new variable is created even if they are called the same. Very important to remember. And then we have placeholders, and this is the missing link, so to say, because as I explained, the whole idea about TensorFlow is telling the computer upfront what is going to happen in all these calculations, but sometimes we just don't know. And we create a placeholder for this, and then the computer reserves some space in the memory, but we are not saying what exactly might be in this placeholder. And for example, here we define x as a TensorFlow placeholder with a specific shape and a data type, but we're not putting into this x any variables at this point, but we will do this here. Later on we have our x data, random variable, a random an array, a NumPy array of random numbers with a dimension 5 to 10. And these x data is later passed as a dictionary. So we have our session with a function. The function is just that we want to find the maximum. It's a little bit strange that finding the maximum is called reduce max in TensorFlow, but this comes out of this tensor perspective, because when you have a tensor, a complicated tensor, or an array, or a vector, or whatever, and you want to find the maximum value in it, then you are reducing your tensor to just a scalar. So this is why it's called reduce max and not get max. So this is the only function we want to run, and then we run our session with this function, and we feed in a dictionary which contains our x and our w, and x and w is called with the data we have defined up front. So you see that here, this is the placeholder x, and this is filled with the data from x data, and the data from x data means as a dictionary that you have a name entry, x, and then your values defined by whatever you put in this placeholder. And a very common practice by creating placeholders is that you are defining the dimensions of the placeholders, but often you don't define all the dimensions. You can have a none parameter for the dimensions, and this is very useful when you're passing, let's say you're passing your input data into a TensorFlow model, but you want to have it independent from the numbers of observations that you're putting into this model. So probably you would use a non-parameter for the first dimension, for the number of rows that you're putting into this TensorFlow session, but you would try to specify the number of variables, because they normally don't change in a model. So you would define how many variables do I have, but not how many data points are passed to the model, and this also reduces the computational costs in the end. So we're more or less done with this. Yep.
In the run session function, the B is not passed.
Yeah.
Yeah.
The B. Yeah.
B, B, B. Where is B?
X, W, B.
Yeah.
It's not a place.
The B
Reduce
is not
max.
passed to the V.
Yes. Yes.
So it takes its default value, or what is?
What we are doing here is the B is here. So we are just passing the data to our session, and this will be then the result of this will be the output. Now, but the B here is defined in the graph. So here we are in the graph. Here we define the graph.
So it takes
So
its default value.
yes, B will be all the time. This is just
It's the intercept.
exactly with the value -1 all the time. So this this is a matrix with the dimensions 5 and 1, and it has the value -1. So it's a constant in this graph.
It's intercept.
So if you don't pass it to the run function, it takes its default value.
It takes the value that was defined in the graph. Yeah. So it would not work, or it would work in a different way if you would take this B up front at the top where the data is defined. Yeah? Then you would define it globally as global variable, but here we define it as a variable that belongs to a special graph. But it's the default graph. So in this example, it should not make any difference if you try it out, or we can try it out. Just have a look. Oh, what did I do?
You didn't run the
I didn't run the things before. Okay. So probably, I don't know where do I have to start.
Somewhere where NumPy is important.
Yeah. I just kicked through all of it. Scopes, variables, placeholders. No, yeah. Okay. So, what are we doing here? We have our x values, and we have our w values, and we are multiplying x with matrix multiplication of x with w, and then we add b. So this is what we want to do. This was the result, and I think if I just take this out here, I think it should work and should give the same results. No, it does not work.
No, it doesn't work.
Yeah, because then it doesn't know that this b is in the graph.
Yeah.
Yeah. So, but if I would pass b here, then it could work again. No.
It's still not in the graph.
No, then it's only in the session but not in the graph. But we need it in the graph because we want to calculate it there. But you don't have to call. So I think this was your question. You don't have when you run the session, you don't have to call everything that is in the graph, because this is defined to be in the graph. But the data you want to feed into the placeholders. You have to specify what kind of data you want to feed into the placeholder. Okay, and then we have a simple example for a linear regression. And this is simple on the one hand, but on the other hand, it's quite a less quite a complete machine learning thing we did in TensorFlow. So we define a number of steps, we define our graph, we define a list for our weights, and then with our graph, what are we doing? We have a placeholder x, and here you see what I meant. You can define none as shape and 3. So we say our x has, we don't know how many elements of x we have, but it has 3 dimensions. It's an array with unknown number of lines, but with 3 variables. So then we have our weights, and we set them to 0 first. We have our intercept, here it's called bias, set it to 0 as well. And then we can try to optimize these initial values later on. So what we want to do is just a linear regression. We have to define a loss function, like always in machine learning. Here it's a very simple loss function. What is this? If you look at this, how would you describe this loss function?
Mean square error of the prediction or the
Exactly.
calculation.
Yeah. So here we have our this is our hypothesis. These are the real values. This is the difference. We take the square and then we take the mean. Now we have our training period. We are using gradient descent optimizer. So I explained it last week. Who could explain in your words what is gradient descent? What is gradient descent doing?
Walking down the graph in order to find the deepest minimum. Basically, if you have a valley or you want to walk down the hill basically to max out the.
And why is it called gradient?
Because gradient is like the slope of the graph.
Exactly. Yeah. So you're calculating the gradient of your graph, and then you're walking down this gradient or in the direction of the gradient with normally very tiny steps. And this is our learning rate. It's quite high here, but doesn't matter. So this is in neural networks still the most common optimizer that you're using, gradient descent. But last session I explained that normally we are using what? Not gradient descent, but stochastic gradient. And the difference between the normal gradient descent is just here you pass all the observations to your loss function and calculate gradients. And in a stochastic gradient descent, you just take a random sample each time from your observations, and this prevents you to go into local minima later on. But this is a linear regression. How many minima do we have for a linear regression?
1.
Exactly, because linear regression is blue. It's the best linear unbiased estimator. So there is only one global minimum, and there's no other minimum in a linear regression. Okay, now we have to initialize all our variables. This is very important if you want to run it. You have to we have defined variables, but now we have to tell TensorFlow that these variables should really be filled with the values that were specified. Then we have our session. We run our session with the initialization of all our variables. So this, all our global variables are initialized here, and then we can just, this is a very common command in TensorFlow, set run init. And now we have our step. Each step is in the range from 1 to 10, so we have 10 steps. And for each step, now we run our session with train, and we pass the x data, the 2 epsilon values, that you have defined where.
Placeholder.
The placeholders, exactly, the placeholders in the graph. And yeah, then what are we doing? We have our train function. Where is it?
Namespace. Short namespace.
Yeah, scope. Train
Name
dash
scope,
optimizer.
train as scope. Yeah.
Here, exactly. And so we are calling the whole namespace. So this means now we have the learning rate and our optimizer. And train here is set as this is the function. Yeah. So it's the function to optimize our loss function. Loss function was defined here. Now we use this gradient descent optimizer to get the results. And we plot, we print the results for every step. So now we have our linear regression done in TensorFlow. And that's more or less all. You can do the same with logistic regression. Then we have here, of course, another function, the sigmoid function. I explained last week that the sigmoid function is used as an activation function in neural networks still many times. But here we use it as part of the cost function or the loss. So where's our loss here? Well, down under. Here, if you look at the namescope loss, you see we have this is the loss function. We need a forward prediction. Where's the sigma function called?
At the top, yeah, where we are generating Y data pre-noise in the first cell. Second last row in the first cell.
Exactly, yeah. So what we want to have, we create our data and throw it into our sigmoid function, and this gives us values close to 1 or 0 then, and then we add some noise to this data, and this is what we want to predict. Yeah? Any questions to this?
What is the difference between the variable node and the placeholder? Is the placeholder only for input data and the variable for evaluated data deeper in the network?
Well, very good question. The placeholder is just reserves a place where you can put variables into it. And the variable is defined. The variable is a placeholder somehow by itself, so this makes it tricky at this point. So the variable means you can you have a variable that has a data type, for example, and during your graph calculation, this variable could have different values.
Yeah.
But the placeholder, in the placeholder, you can call different variables from the same. They should fit to the placeholder. But the difference is it's like a meter variable. You're saying at this place there will be later a variable, but you're not defining the variable.
Okay.
Good. Then I got I uploaded another Python script, and this is taken from the book as well. And I would like you to have a look at this code. You can scroll down it or make it bigger or whatever, and try to understand what is happening here. And I tell you a little bit what the program is meant to do, so this makes it easier for you to understand what is happening. And then we would have, not much, but a little bit of time where you could try to explain what is going on in this code. So the idea of this code is we want to make a text classification, and we will use a long short-term memory network. We don't have to worry about what it is right now. We will touch this next session to get the, or perhaps we should do it the other way around. Perhaps I should explain what a long short-term memory is. You take this code, I explain what this code is doing, and as kind of homework, if you have time and fun to do it, you first should run this code, understand this code, and try to change the code that you can run it on a different example. So what this code is doing is it creates a simulated text data set. And the texts are created in a way that you just take random numbers from 1 to 9, and then take the word of the numbers, like the word 1, the word 8, and so on, and create sentences out of these words. The sentences are of different length, and then you first have to get them all in the same length. So in this example, I think the maximum length is defined as 6 or so. So you might have 6 words in one word, like 2, 3, 1 or so in one sentence. And if you have less than 6 words, then the other numbers, missing numbers, are filled with the number 0, and the number 0 then is transferred to the word pad. Because what we're doing there is padding. The problem with natural language processing most of the time is somehow we have to define the dimensions of our tensor. And if you have sentences that are different from different length, we are running into a problem. So what you're doing normally is that you are taking the longest sentence and you are expanding the other sentences with a word like pad or something like this. But then you have to remember how long was the original length of your sentences, because you don't want to train your algorithm on pad. So you have to somehow fill the tensors that you can work with them, but you don't want to run any calculation on these words. Therefore, you have to remember the length of the sentences. When this data is created, we have 2 labels for our data in this example. One label is it's even or it's odd. So the whole number is even, of course, if the last word of this sentence represents an even number, and it's odd if it represents an odd number. So it's a very simple, silly example, and every human, of course, can classify these sentences without any computer program for this. But it has many interesting features in it, because, for example, we're using a stochastic gradient descent, which always leads to serious problems when you try to implement it yourself, because then you have to, I don't know, if you ever had a look at TensorFlow, you probably did the MNIST data set. So it's the standard data set where you have handwritten numbers, and you have to build a classifier that is identifying these handwritten numbers. And it is implemented so well in TensorFlow that there is already a data set for all the mini batches that you have to use for stochastic gradient descent, so you don't have to program it anymore. And within 5 minutes, you just can have your MNIST code running, but you don't really see what is going on there. And this example is a little bit better because we define our mini batches. Mini batches are for the gradient, stochastic gradient descent. So you have to have a function that somehow identifies which observations are used for training in the actual step, and which are mini batching is in. We have in this code, we define our own loss function. It's a logistic regression, but nevertheless, we define our own loss function. And we use a quite sophisticated deep learning algorithm in the code, a long short-term memory network. And this is very easy. So this is just this part in the end. We define a long short-term memory cell, and we have already a function in TensorFlow that we can call, and we just use the basic long short-term memory cell, and then we just defined the hidden layer size and set a forget bias. So it's very easy to run really sophisticated deep learning models in TensorFlow, but you should know what these models are. And therefore, we already talked about the projects. We get still quarter of an hour or so. So I will just switch to a slide I prepared to show you what a long short-term memory is. But really use this code at home, try to understand the code. This is the first thing you really should do. And then try to create a new example. I would suggest you take the Gutenberg corpus that we already covered, take the text from Alice in Wonderland, let's say the first 1,000 sentences, and the first 1,000 sentences of Shakespeare's Hamlet, which is in the Gutenberg corpus as well, and rebuild this model with real data. And this really becomes demanding. It's not an easy task. And, I will try to do it myself, and then we can share our codes next.
But what should it classify?
Is the sentence from
The
Alice
one
in
on the-
Wonderland, or is it from Hamlet? Just want to create screenshots of the slides so that I can put them together in video. So now it should work. Yeah. So this is a normal artificial neural network. Yeah, we have here two Y nodes in our output layer with 3 inputs, x1 to x3. This is what we already covered last time. And for many years, well, deep neural networks are not really very prominent for many years, but we used to say that you start to do deep learning as soon as you have more than 4 or 5 layers in your network. And deep learning was just thought to have artificial neural network with a lot of hidden layers. But this is not really what is deep learning about. This is how one neuron normally looks. So this is what we would do in one neuron. We have all our inputs, we have the weights for the inputs, we have our transfer function, which is normally a sum, and we have our activation function, which might be sigmoid function, or a tan function, or a real function, or whatever. And then this neuron is spreading the signals to the following neurons. But you could change the structure of this simple neuron to a recurrent network or a recurrent neuron. The idea is, here we have our inputs x, and we have still our output y, we have our summation function, and we have an activation function, but we transfer our outputs via a loop to the inputs again. And this, of course, only makes sense if there is something like timing. So what we want to do is, for our first observation, for the first value of x, we have no loop effect, but for the second value of x, we have the result, the output of our neuron, put into the neuron of x2 as an additional input. So this representation, this is the short version, so this is what really happens. So you have t minus 3, you calculate an output, the output goes as an input into t minus 2, and this as an input, and so on and so on. So at t, we have always the output of t minus 1 as an input. Yeah? You get this idea? And of course, we could do the same, not just with one neuron, but with layers of neurons. So here we have one layer, and all the outputs from these layers are going back into these different neurons. But it's still the same thing. Now we can introduce something which is called memory cells. The picture looks the same, but the idea is that we are evaluating these loops from one input to another input, and perhaps we give them additional weights, and these weights might be active or not active. So there might be an input from a further node or not, and with this you even can stretch it over time. So here, in our picture before, our x2 only got the information from the output of x1. But if we introduce memory cells, this means that the information from x0 at this point is still somehow contained here into x2, but over the way of x1, and how this memory cell has remembered to still use the information from the first cell.
Is this network then processed from 0 to 2, like diagonally, or is all the values evaluated at the same time, and then the memory effect happens across?
So the point is, normally it still looks like this.
Yeah.
So you have this neuron gets all the x values. So there might be x1 in the mini batch, and then next time x2, and so on and so on. But what is happening is that you are feeding the data into a time-ordered sequence. So you are not feeding the value for x5 first, and then the value for x1, but you have x1, x2, and so on and so on. And it would be the same like adding more layers to the network. Because here you have our x0, and you already calculate an output from x0, it's y0, but for the next observation, you have this effect, this memory effect, that somehow some information from this was remembered here. And here you have an output, but you still have this remembering effect. Perhaps it even gets more clearly when we directly look at the most complicated stuff, the long short-term memory cell. So this is a long short-term memory cell, invented by Hochreiter and Schmidhuber here at the university in 1995. And this is what really is driving Google algorithms in many parts. So what do we have here? We have here our x values, ordered by time. What happens? These values, now these are all different neurons that we have. And all these connections, they have weights, and all these weights are trained in the neural network with normal stochastic gradient descent process. But all these connections now have different functions. We have, first of all, a connection that somehow goes from x to y. So this means our whole long short-term memory cell is still producing, based on every x, kind of output y, which means it is either activated or not. We have two different activation functions. We have a logistic function, and we have a tangents hyperbolicus function. Who knows this function, and what is the range of this function? 1 minus 1. And this is the important thing. So we have one function, which is a sigmoid function with a range of 1 to 0, and one function with a range of -1 to 1. Now see what happens. Where to start? We get our output gate. So over this way, we calculate what is really here. There's no connection here, so this defines our output. We have here this normal neuron that we have with a sigmoid activation function, and this gives a value to our output gate. And what is the output gate? The output gate multiplies a value that comes from here, and this value is calculated with a tan function, so it's either, it's somewhere between 1 and -1, and in extreme cases it's 1 or -1. So this makes our input here positive or negative, and is then put to the output. But the same output is also passed to our next cell, or to the same cell, to the next data point in time. These informations flow into all these neurons again. So for example, as well in our output neuron. So if we had a negative value here, we get this information here, and even if we have a positive value then here, then this value is here in the summation part somehow reduced by the negative value that we had before. And perhaps you get the idea. So this means if I have a negative output first, and then the next output, even if it is would be positive, if I just take my x values together, it might become negative because the network somehow remembers that we are in a negative cycle. To make it as a picture. So, but this information also goes, for example, in this neuron. And this neuron feeds our forget gate. What is the forget gate? The forget gate, here this is the multiplication. The forget gate takes here again the input, but transferred in a tan function, so it's again -1 or 1, and takes this output of the forget gate as an input for the next forget gate. And if this here becomes negative, then the effect is that information from one data point to the next data point is less of this information is stored. And if it becomes positive, more of the information is stored. And so in the end, this means by training these weights here, you can train the network to forget what it has already learned from previous data. And then we have our input gate here, which we need. No, here we have the inputs of our. So this is more or less the normal inputs that we have. It's the same value like here, but we do something else with this. We multiply them with a tan function output. So this gets positive or negative, and then it gets added to what we had already remembered from the first indices. Yeah, I think this is more or less the idea. I think I touched everything. So this is very, very useful for text data. Because if you feed in now for x might be one sentence, but you feed in the first word, then the second word, the third word, and so on. You got some of the information that was somehow combined with the first word when you're evaluating the second word. And there are so many ways where this could be useful. For example, we have seen that words have very different meanings. The same word, the word bank, might have very different meanings. But if you have already some memory of what the words before the word bank meant in this sentence, then you probably get a better idea in the network what the real meaning of the word is. Or you see it when you are typing into Google, then Google is proposing you what Google thinks you want to type into the search engine, and the more characters you add, it changes, because the more information Google gets, the more information this long shorter memory cell remembers, and therefore the better gets the result in the end, hopefully. So this is really deep learning then. And of course you can combine these cells in many layers. You can have a long short-term memory cell on top of another long short-term memory cell and so on and so on. This was the original algorithm. Lately it was a little bit simplified, and this is a GRU cell now. So, and this GRU cell, it has more or less the same idea, but the mathematics are easier, and there's big discussion going on if you can represent everything that you could represent in a long short-term memory network in a GRU cell. This is probably not true, but definitely you can represent everything that is in a GRU cell in a long short-term memory cell, which leads to the situation that Jürgen Schmidhuber still claims that he has invented also the GRU cell.
Subset.
But this is his problem, I think. So yeah, you get an idea of this. Please have a look at this code example and really try to get hands on it. Because if you are able to use this example to build a new classifier, and you can start very simple and say, well, let's just, for example, stick to the two classes problem, but we add different input data. You even could start with adding input data from a structure that is quite similar. For example, always take just the first 6 words of a sentence. So, and then you can increase the complexity of the problem, put into it longer sentences, and then you will see that you have to change some things of the codes and so on and so on. But if you are managing to do this, you have a state-of-the-art text classification system on your laptop where you understand everything that is really going on. Thanks.